So we need to decide where we want to be on the capital allocation line. And to do this, we need to do a little bit of algebra and a little bit of calculus. The way we want to think about this is that an investor chooses Y, the allocation between the risky and the risk-free, in order to find the best combined portfolio C star, which maximizes utility. So first we need to do a little bit of algebra. We need to get the right-hand side of the utility formula in terms of a simple choice value Y, and then our investment universe. So here is our utility formula. It's equal to the expected return of C minus A times the risk of C squared over 2. Here is an equation for the return of C, and here is an equation for the risk of C. I'm going to first substitute the blue for the blue and the green for the green. And this is going to leave me this equation. I'm going to do a little bit of algebra by pulling this over, and then this allows me to substitute in for Y. And so now I have my utility equation as a function of my investment universe, which is the risky asset and the risk-free asset, and my choice variable Y. So my investment universe is defined by the risky asset's return and risk, and the risk-free asset return, and my choice. And so I have a functional form where I can choose Y, and our inputs are just this investment universe, which is given. And so to maximize the utility, I need to take the first derivative of U with respect to Y, set it equal to 0, and then solve for Y. And so since Y is the variable, our F goes away. I have Y to the first becomes 1, and here I have Y squared. I bring the 2 down, subtract it using the exponent rule, and I end up with this. Simplify slightly, 2's cancel, I get rid of the 0, I drop the 1, and here's my equation. Now, I want to check to see if this is a maximum or a minimum, and the way to do that would be to take the second derivative. That would drop out everything except for the A sigma squared P, since A is a measure of risk aversion and is a positive number, and since sigma squared must be a positive number, I put a negative sign in front of it, and I can see reasonably quickly that my second derivative is negative, and therefore this is a maximum and not a minimum. So I set this equal to 0, this equation, and I solve for Y. I pull this over, drop this down, and I get that Y star is equal to the expected return of the risky portfolio minus the risk-free, it's essentially the risk premium, divided by the variance of the risky portfolio times A. And this is a Y star and not just a Y, because this particular Y defines the C star that maximizes utility. That is why this is an optimum. Okay, let's examine this equation. Let's examine this Y star equation. Y star is the optimal allocation of the risky portfolio P in the combined portfolio C. Again, it's an optimum because it maximizes utility. Note that if the return of the risky portfolio gets bigger, Y gets bigger, which means I put more money into it. If the risk of the risky portfolio gets bigger, Y gets smaller, so I put less money into the risky portfolio. And if my risk aversion level gets bigger, if I'm more risk averse, then Y gets smaller. I put less money into the risky portfolio. Okay, let's pick some numbers again. Let's go back with our risky asset of 10%, risky portfolio with 10% return and 20% risk, and a risk-free of 3%. And we're going to choose this for an investor whose A equals 2, and we're going to solve for Y star. And so I'm just going to plug into my equation that Y star is equal to the risky portfolio return minus the risk-free divided by A sigma P squared, 0.1 minus 0.03 divided by 2, which is the risk aversion for this investor, times the 0.2 squared, and I get 0.875. And the way I interpret that is the optimal allocation for this investor is to put 87.5% of wealth in the risky asset and 12.5% of wealth in the risk-free. So now that I know the allocation, I can now solve for C star, defined by its return, its risk, and I can solve for U star. So I'll solve for these three things. So the first thing is the risk of the return of the combined portfolio. That's 3% plus 0.875 times 0.1 minus 0.03, and I get 9.125%. And the risk of this combined portfolio is 0.875 times 20%, and I get 17.5. And the utility that I achieve from investing in this portfolio is going to equal this utility value. It's now optimal. This is the maximum utility, and that's going to be the 0.0606, or 6.06% is the indifferent or certainty equivalent rate. And here it is on that graph. And I can see where C is. I'm 87.5% away along this line. I have a return of 9.13 or 9.125 and a risk of 17.5%. And here I've just drawn in the utility curve with that intersection point. And then just back to my recap table, I know that when I was at 40% in the risky, I achieved a utility of 0.0516. When I was at 75%, I achieved a utility of 0.06. But now that I'm at 0.875%, I achieved a utility of 6.06. And so this is the highest possible utility achievable along this curve. If I were to go further to the right and put more money in the risky, I would end up with a utility curve that was below this curve. Now we could show through trial and error by entering in more values of y that for this investment universe defined by this risky and risk-free, and for this investor defined by A, that this y produces the maximum utility. I could just keep plugging in different values of y given these outcomes and show that I would get smaller and smaller values of u. But I don't have to do that because we did the calculus. What about a different investor? What about a different investor faced with the same investment universe? So remember, at this point, investors are defined solely by their risk aversion level A. And so instead of the old risk aversion level of A equals 2, what if I have a risk aversion level of 7? So the first thing I do is, given my investment universe, which is defined by the risky asset and the risk-free, I calculate the Y star for this investor. The difference is this investor has a risk aversion level of 7, and I get 0.25. Before I had a Y star that was equal to 0.875. This is a different investor. Now I get a Y star that's equal to 0.25. And so 25% of wealth in the risky, 75% in the risk-free. Again, I calculate the return of the combined, the risk of the combined, and the utility from the combined. And I'm going to see that I end up with a return of the combined portfolio at 475, a risk of the combined portfolio at 5%, and a utility of 3.88%. And here is the graph for this person. Now note that their C is further to the left down this curve. That is because they are more risk averse. And so every different investor is going to have a different level of risk aversion and a different allocation of the risky in the combined. They're going to have a different spot on this line. So this is the investment allocation set for everyone, but depending on how risk averse they are, they're going to choose a different spot. The more risk averse, the closer they'll be to the risk-free, and the less risk averse, the closer they'll be to the risky portfolio. So note that Y decreased as A increased. Increased risk aversion means a lower risk optimal combined portfolio. Okay, last thing here. Let's compare the maximum utilities for the A equals 2 investor and the A equals 7 investor. Which is better off? Well, for the A equals 2 investor, we ended up with a utility of 6.06. And for the A equals 7 investor, we ended up with a utility of 0.0388. This is a trick question. You can't compare the utilities across investors. You cannot say that this investor is better off because this investor has higher utility than this investor. Each investor is at their maximum. And that's the goal, is for a given investor and a given investment universe to maximize utility. And that's what we've done.